Hello guys, this question is taken from Pathfinder, a rotational motion. They gave that a rigid tube is welded along a diameter of the uniform cylindrical pipe of mass m and radius r. The pipe is kind of hollow and its mass is m, and a bead of mass m is connected by two identical light springs, each of force constant k. So the stiffness they gave for the spring is k. And it can slide inside the tube. So the bead can slide inside the tube. So the inside pipe is, they told that it is light, identical light springs, and slide inside the tube shown in the figure. So I think the pipe is massless. I think they did not give. I don't know. They gave for the springs. Springs are massless. Light rigid tube. Yeah. So the pipe is the massless, and the springs are also massless. Other ends of the spring are connected as shown in the figure. So we can see the figure. So let's just redraw this figure here. So inside this is a tube, and this must be the center, and they gave here, they told they both are identical, then it must not be the equilibrium position. Let's see. Other ends of the springs are connected to the pipe as shown in the figure. The pipe is held motionless on a horizontal floor. So the bead is pulled aside a distance x away from the center of the pipe. Yes, obviously the center will be the equilibrium position, but they pulled it away the distance x. So they pulled it away the distance x, so there must be a force acting on that thing, kx from this spring, and the same thing will happen from the other spring kx. So there will be 2 kx force will be applying on that small mass. Let's see what else they give. And then the pipe and both are released simultaneously. If the cylinder rolls without slipping on the ground, find acceleration of its center immediately after the system is released. So what can we do? They are asking the instantaneous acceleration of the pipe, not the center of mass of the pipe and the bead both, but they are asking the center of mass of the acceleration of center of mass of only pipe. So what can we do? Let's see what can we do. There is a spring here. There must be a force acting on this block from the small spring, that is kx. Actually that is a normal spring as that also, but it is compressed and that is elongated. The other one is another kx. Both 2 kx force will be acting on that other ones, but from this spring there will be a reaction on that pipe, that is kx, and also there will be a reaction from the other spring, that is kx. And we should not forget that is there is a floor too. From here we can say it is rolling in this side, so there will be a frictional force acting to this side. So there will be some frictional force. Let's solve it. First of all, uh, we can write the forces which are acting on the pipe. If this is the pipe, there is 2kx force acting on this pipe, and there is a frictional force acting on the pipe, both in the front side. Sorry, both are acting in the front side. There is some frictional force, so we can say 2kx plus frictional force is equal to capital M into A. Let's take the acceleration of the center of mass as A. So there will be an acceleration A. What else can we do now? We can take it as an equation 1. Yes. Another one we can do is, from the center of mass frame we can write the torque for the pipe. What can we write the torque? So from the center of mass frame, there will be mg here acting on the downward, and also there will be some normal force, and this small bead is having some acceleration downwards. We don't know the acceleration a naught. Let's take it as a naught. If we write torque for the sphere, we can write it like, there will be a normal reaction. This is the action, but there is also the reaction of that normal force on the pipe acting down here. So we can write like normal force at a distance of x minus frictional force acting on the pipe in the opposite direction. If this is the anti-clockwise direction, this is the clockwise direction. So Fk into radius is r. Now we need to write the torque. What should we take the moment of inertia? I am asking you guys the question. We can take alpha as alpha, but what to take? Should we take the combined moment of inertia, or should we only take the moment of inertia of the pipe? Should we include the bead too? The normal force here itself is coming from the bead. The acceleration and we can write mg minus n equal to m into a. So the normal force itself is coming from the bead, so we are not going to include the moment of inertia of the bead, because the rotation is happening. All these torques are acting on all these forces are acting on the pipe itself. So let's take mr square. That's it. Mr square is the moment of inertia of the pipe through its center of mass. So if we take it as equation 2, what can we do as equation 3? If we take the small bead, there are some forces acting on that bead. Let's take that bead like this. This is the bead. I'm sorry. This is the small bead. There is some normal force acting on this direction. There is mg acting on this direction. Mind you guys, this is small m and that is capital M. Usually I'll be confused in these things, because I don't care about these things as much as I'm solving right now, because I just care about thinking. In that thinking, I just do mistakes taking capital M as small m and all these things. So also there will be some acceleration a naught, and the a naught is nothing but, if we see in this thing, I'll draw it again. So there is alpha, the angular acceleration, and this is the center of mass. And if you see from here, this is downside, it is x distance, and the acceleration is nothing but alpha into x, which is equal to a naught. So a naught is nothing but alpha into x. If we write the equation for this, mg minus normal force into small m into alpha a naught, which is nothing but alpha into x. If we take the third equation, let's solve all of these three. So 2kx plus fk equal to m into, let's take the acceleration as alpha into r, and let's then we'll solve it for acceleration alpha. Let's solve it for alpha, and then after we can get the acceleration. So yes, we can take friction. To this, let's multiply it with r, both sides multiply it with r, and add it with add the equation with 2, then frictional force will be cancelled. So 2kr plus fk into r equal to m alpha, I told it small m and capital M at that case, so let's go with small r square, because that's what they gave in the question. But now let's add it with the equation to n into x minus fk into r equal to mr square alpha. If we add both of them, fk will be cancelled, so 2k, what the hell, x into r, so 2k x into r plus n into x equal to 2m r square into alpha. This is what we got, but we have to eliminate this n here. So n is unwanted value here, so let's just eliminate the n from this equation. So let's take this equation, mg minus m alpha x is equal to, what the hell, this is capital M, this capital M here, equal to normal force. If we keep this value here, we can just solve it just like the 2kx into r plus mg minus m alpha x equal to 2m r square alpha. So, and multiplied with x outside, we can send the 2kx r, multiplying the x inside mgx, and multiplying and send it that side, equal to 2m r square alpha plus mx square alpha. 2kx r plus mgx equal to alpha taking outside 2m r square plus mx square, and just sending it this side, 2kx r plus mgx divided by 2m r square plus mx square. This is alpha, but in pure motion we know r into alpha is acceleration. Why alpha into r is equal to acceleration and all that, I think you must be knowing the concept if you are watching this. If you don't know, I'll make a video on it, another one. 2kr plus mg, taking x common out and multiplying it with r, 2mr square plus mx square equal to alpha into r, which is acceleration. So acceleration is nothing but x into r, 2kr plus mg into 2mr square plus mx square. This is the acceleration. And in this case, I think in this case we wrote two equations from here. I think we can do it from the perspective of the ground too. I think if we do that from the if we write the equations from the ground frame, from this center of rotation, instantaneous center of rotation it is, we can still get the answer. So okay, second method, let's see. Let's do it in a second method 2. So we know here normal force, it will be acting, and there will be some 2kx, and there will be frictional force which we don't give we don't care, and there will be mg, that also we don't care, and all we care about is what is acting on that, what is acting as a torque. If it is passing through the center, we don't even care about it. So let's write the torque for that one. 2kx into r plus n into x is equal to mr square. Is it mr square? No. The moment of inertia changes from this center of rotation. Just apply the parallel axis theorem. So it will be 2mr square into alpha. Alpha won't be changed. Alpha won't be changed if you know the concept. But we have a problem here. What is n? The same story. The alpha is this. If we write the equations for small one, again the same story. Let's take this as mg, and this is normal force, and this will be alpha into x. Mg minus n equal to alpha into x into mg minus m alpha x equal to normal force. If we keep this value here, we'll get the same answer. Let's just solve it. 2kxr plus normal force. In place of normal force, we got mg minus m alpha x. Mg minus m alpha x into x equal to 2mr square m 2mr square into alpha. 2kxr plus mgx equal to, sending this that side again, same story, 2mr square plus mx square into alpha. If we take the x common out, 2kx plus mg into, we got x here, divided by 2mr square plus mx square. This is alpha, and if we multiply it with the radius, we will get the acceleration. That is nothing but 2kx plus mg into x into r divided by mr square plus mx square equal to alpha into r, which is acceleration. So this is the answer we needed. Thank you.